All right, welcome to The Explainer. Today, we're basically cosmic detectives. Our mission? To hunt down a really mysterious number and uncover its secret identity. A shape that's hidden away inside of infinity itself. So, like any good mystery, it all kicks off with a simple question about a very specific and, let's be honest, a completely random-looking number.
So this is it. This is our culprit, the MRB constant. It's just a string of digits that seems to, well, exist. It's not famous like pi or elegant like the golden ratio. It just kinda is. So where on earth does it come from?
Well, it's born from this beast of an equation, an infinite, alternating series that just keeps going and going forever. It looks like total mathematical chaos, right? But what if it's not? What if this isn't just a formula, but more like a blueprint? Okay, so to crack this thing open, our first clue isn't buried in some crazy algebra. It's actually hidden in simple geometry. We need to figure out the shape of a root.
Think of this as our Rosetta Stone. It's how we translate this abstract math into something real, something you can almost touch. This expression, x to the power of 1 over y, isn't just a random calculation. It's the recipe for finding the edge length of a shape in any dimension.
I mean, think about it. We all kind of know that if you have a cube with a volume of 8, its sides have to be 2, right? Well, the math checks out perfectly. 8 to the power of 1/3 is exactly 2. So the formula works. It's a solid link between what's inside a shape and its most basic measurement.
So, with this geometric key, we can basically build ourselves a ladder, one that's going to let us climb from one dimension to the next, checking out a brand new shape on every single rung.
Now, here's where it gets really cool. We can finally apply this clue to our chaotic-looking series. We're going to create a special family of shapes. For each and every term in that series, we'll build a geometric object, a hypercube, where its content is the exact same number as its dimension.
And just look at what happens. In dimension 1, we get a line of length 1. In dimension 2, a square with an area of 2, which means its edge length is the square root of 2. Then a cube with a volume of 3, giving it an edge of the cube root of 3. You see the pattern here? All of a sudden, those numbers from our mystery series aren't just numbers anymore. They are the actual edge lengths of a unique hypercube in its very own dimension.
Now, this part of the journey is pretty easy to imagine, right? We're just stepping from the familiar, flat world of a square into the three-dimensional space of a cube. We can all picture that.
And here's the next jump up that ladder. From our comfortable 3D cube, we take a leap of imagination into the fourth dimension, to the tesseract. The key thing to remember is, each of these shapes has an edge, and each edge has a very specific length.
And bam! Just like that, the secret's out. That chaotic formula? It's not random at all. Each piece, the square root of 2, the cube root of 3, the fourth root of 4, it has a secret geometric identity. It's the measurement of a side of a specific hypercube.
Okay, now for the chase. We've identified all the individual pieces. So what happens when we put them all together, following the original formula's instructions of adding one, then subtracting the next?
You've got to picture this as a kind of infinite balancing act, a cosmic tug-of-war. We take the edge length from the first dimension, then pull back with the length from the second, push forward with the third, and so on, back and forth across an endless ladder of dimensions.
Let's watch how this plays out. We start at 0 and add the 1D edge, which is 1. We're at 1. Then we subtract the edge of our 2D square, landing us deep in the negative. Then we add the edge of our 3D cube, which jumps us all the way back up past 1. Then subtract the tesseract's edge. I mean, it is a wild ride.
But here's the really amazing part. Even though it swings all over the place at the beginning, this infinite push and pull starts to calm down. The jumps get smaller and smaller and smaller. The sum doesn't fly off to infinity or just bounce around forever. It slowly, steadily converges on a single stable point.
And that final destination, that precise point where this infinite dimensional tug-of-war finds its perfect balance, well, what do you know? It's our mystery number, the MRB constant.
So here we are, the big reveal. We've cracked the case, and now we can finally give our number its true name, its real identity, based not on its formula, but on what it actually means. And this is the whole point. The MRB constant isn't some abstract mathematical fluke. It is a physical, geometric measurement.
It is the final result you get when you compare the edge lengths of this special family of hypercubes in this infinite alternating series. And hey, this isn't just some fun interpretation. The mathematician who actually developed this theory, Marvin Ray Burns, says it himself. The constant is a direct representation of this geometric comparison.
So our strange little number is actually a fundamental property that just emerges when you line up and compare an infinite number of geometric worlds. It's a measurement hidden in the very fabric of dimensionality itself.
Which just leaves you with one final tantalizing question, doesn't it? If a number this obscure has such a profound geometric meaning, what other secrets are hiding in plain sight? What other fundamental constants are out there just waiting for us to find their hidden shape?